After we take the transpose, it will become 100 by 784. And this is, let's pretend, 10 by, sorry, after we take the transpose, it will become 784 by 100. And this is 100 by 784, right? Anyway, so this will come out to be 10 by 100. So far, so good. So if you take a look at this 10 by 100, right? That means there are 10 rows. Each row has 100 columns. Okay, B, we will leave it to be just 100, an array of 100. So what it does, it adds this to every row. So this does not have to match the, was that the question? Okay, so anyway, let's take a look at the batch norm computation now. Okay, so once again, let's assume our S matrix has 100 of these. So there are 100 numbers, and basically there are 10 rows. Okay, so we have to compute the mu and the sigma, right? So see if this line makes sense. Self.mu equal to np.mean, self.s, x is equal to 0. So what will it do? It will basically do, rho is the axis, it will start to average all of this data. Okay, so we will left with, the average will come out to be just 100 numbers. Okay, same thing, this will automatically compute the variance, so we don't have to do anything. Okay, one thing I forgot to cover in the last lecture was, and let me try to explain that. And maybe Damien, that's why you were not getting the 90% accuracy. Okay, so in the forward pass, as you guys saw, so this is for batch norm. Okay, we feed in, let's say, a batch size of 10. 10 x's, right? So if the batch size is 10. Okay, so then for these 10, we compute the mu. For these 10, we compute the variance. Okay, then once we are done with it, we move to the next set of 10. So we compute another mu b, we compute another variance b, correct? And then whatever, compute the delta and so on based on that. Okay, so suppose we are done training. If you take a look at the neuron now, okay, the neuron has, let's see, a sigma over here, SI hat over here, gamma, beta, activation function, right? Okay, and you can see to compute SI hat, we need the mean of the batch and the variance of the batch. Everybody agrees? Okay, so we did the training, we adjusted all the weights, it's ready to go. Let's go to the test time now. Okay, if I feed in some unknown data over here, at the test time we don't feed batches, we feed one at a time. So what mu and sigma it should use?
From the last training one, right?
No, you should skip that part.
No.
You don't need it. You just need the weights.
No, we need to keep the mu and mu b sigma p, sigma square b. So the question is which one? If we did not do anything, what we will do is the very last batch that we have passed through, because we were storing these, it will use those. But that's not accurate. That's just mean for the last batch.
Mean for the
Another
batches.
Yeah, one possibility is mean for all batches, sigma squared for all batches. Anyway, people have done a lot of studies on batch normalization algorithm, and they have found is for test time, use running average during training. So, just like you guys saw in momentum or in Adam algorithm, so what we'll do is we'll go every time we compute. So we'll also store mu b running and sigma square b running, which will be simply the old value of mu b running,
So we are accumulating all the
0.9 plus 1 minus 0.9. So this is basically our momentum type of factor over here, mu b. So the current batch, whatever it is, it will be added a small percentage to the whatever our old value was. So during training, we'll keep updating this, Okay, during test time, this is what you'll be using as you pass the data through here to compute SI hat. You'll be using the mu b running, and then Damien, if you did that, you'll see a significant difference. Okay, so anyway, let me go to the code now.
Professor, can you explain the low level line of it, like using for loops? Because I'm doing all of that in one single way code. I'm not using the classes first. So what for loop would we be changing for that?
If you're using the old way, old way, then you should pass it twice. So once you have a loop of 10, whatever that batch size is.
Mm-hmm.
So first pass it through and just compute mu b and sigma square b. And then run it again, the same 10. Then you will be able to do SI hat. So don't try to compute SI hat on the first time through. But like I said, the easiest way is, because we'll be doing it this way as we go and start doing more tensors, is, like I said, it's really a 5-minute change. All you're doing is removing those ones. Wherever we did comma 1, just remove those. All sizes stay the same. And then focus on just 3 or 4 places where you were multiplying matrices to make sure that proper transposes are there, so that your data becomes batch size times whatever, the number of neurons in the layer or whatever. And I'll give you the code and you can compare it to see where the change is, and really it's not more than 5-minute change.
Professor, let's say that we have 1,000 training data, so each batch will be 10, like the batch size is 10. So we need a for loop for 100
Correct.
to feed.
Let me show it to you. So yeah, that's a good question, and you'll get this code. So let's take a look at the training part. Just your question. Okay, so if you take a look over here, just focus on this part. So this is same as before. Okay, same as before we did the shuffle. Okay, so for example, what will this go through? How many times? If we have 1,000 training, right? This loop, as you can see, will go 0 through 1,000, right? But then we added one more, pretend batch size is 10. So basically what it will do is I will vary 0, 10, 20, 30, and whatever, 990. This is how the I will vary. Every time I varies, take a look at this statement now. Okay, so what we are doing is xtrain mini is basically I colon I plus batch size. So in the beginning I 0, this will become 0 to 10, right? So using the range operator, we are able, so this will be 0 through 9 basically, very first time through the loop. When I becomes 10, then what will happen over here?
10 to 20.
10 to 20 or 10 through 19, right? So this way rest of the code now will use this matrix over here, xtrain mini or ytrain mini. Okay. So we don't need any other loop, like a double loop or whatever. So that makes it a lot easier. Anyway, so okay, so let me take you very briefly the key concept. Okay, let me go to the evaluate function first. Okay, so every time we evaluate a layer, let's see if this code makes sense. I'm using a Boolean variable to decide whether I'll be putting a batch inside the layer or not. Okay, so if it is training mode, right, then this, as we already talked about, because our S will be, for example, 10 by 100 in the first layer if we have 100 neurons. So we need to create the mean, so mean will be done on x is equal to 0. So this will give us sigma square b, this will give us mu b, right? Then later on I will do compute si hat, okay, or I called it s hat because it's for the entire column. But let's see if this makes sense. Running mu equal to 0.9 self dot running mu plus self dot mu, right? So as we discussed, because at test time we'll be using the running mu, but during training time we have to keep updating it. Okay, so we have the mu and the sigma. Okay, now what else do we need to compute? We need to compute S hat and SB. So does this formula seem right? S minus mu B over K NP dot square root sigma square B plus epsilon. So you can see just one line of code will compute S hat, and then one line of code, gamma plus beta, will do that. Okay. So that's during training, right? Okay, so remember our beta and gamma are also parameters that we start randomly that the system will learn. So once we do the gradient update, so there will also be, so if I go to the network class, okay, update gradients and biases. Okay, so over here, 2 extra lines will be added. Beta minus learning rate. So let's make it a little bit smaller. Okay, so beta will be updated in the beginning. It will be randomly initialized. Gamma will be updated. D beta, D gamma will be computed according to our equations. Remember, I think D beta was simply as the delta, D gamma was delta times SI hat, right? Okay, anyway, once you get the code, try to go through it. It should work, so let me give you now a few. Okay, so or let me do this. What I'll do is I'll give you the whole code, so it will be completely running. Once again, don't use it, modify your own code. But if you totally get stuck, because I don't want you to spend too much time over here, then look at the code, make your code work properly. But anyway, let me just quickly run it. Okay, so to run it, I simply have a variable over here, as you can see. do batch norm true, which I pass it to the training method. So if I want the batch norm, otherwise it will simply skip so that we can compare the difference it has with the previous code. Okay. For our data set, because our data set is in a way kind of difficult. You saw last time also, you were not seeing too much variations whether you use the sigmoid, but gradually as we keep our things more involved, you'll start to see the difference. Even in this case, for some of you who were able to successfully implement Atom, you will see a significant difference in Atom. Okay.
On the learning rate.
What's that?
On the time it takes to converge, yes.
Correct. If you use Atom, you'll hardly need like 10 epochs
Yeah.
to get the same answer, right? What was your 12, maybe?
Yes.
What did you say, 12?
Yeah.
Yeah. Anyway, I'll show you how that works. But anyway, batch norm for this particular data set will not show you a big difference. Okay, it will be pretty similar. So if I use 50 neurons, one thing with batch norm is the bigger the batch size, the better it works. Okay, so if you used, for example, a batch size of 50, you'll see it's first time it's loading the data may take a second or so. Second time I run it, it's typically pretty fast. So when I did it with the batch norm, I was getting around, let's see, I think around 89% accuracy with batch norm. Okay, and batch size of 50. Okay, so yeah, at RAIN you'll see 89.23%.
I can get 91.
With the batch norm? Excellent. Okay,
I didn't see the code yet, but I don't see any evidence why we cannot just go through the batch and then do the gradient update at the end of the batch.
repeat your question, I didn't follow. If
Instead of passing through the whole batch, we can do it one by one, just accumulating it, and at the end of that batch, let's say 50, you calculate mu, you calculate sigma, and then you do the gradient update.
Oh, I see. Rather than converting it to this form, but if you have to do, so do you store those values so that you can go back and compute?
Yeah.
Yeah, so you could adjust it accordingly. Yeah. So it's not like this will give you a different result, it's just more convenient. Okay, so anyway, the biggest difference, like I said, what you will notice is with the atom. So if I, don't worry about this. Okay, and let me comment this out. Okay, so now if you go to Atom, and I eliminated the batch norm so that we can see the effect of Atom. And by the way, Atom implementation, let me just, for the benefit of those of you who are having a little bit of difficulty, how will you implement Atom? Again, it's very easy. If you go to the original equations, so remember our reference article was this one where you had studied the different learning rate schedules, including Atom. Okay, so anyway, if you go to Atom, so those are the equations, right? So MT equal to beta 1, so beta 1, beta 2 are two parameters. I forgot, we typically use 0.99 or something like this, right? Okay, GT is basically the gradient. So this could be the gradient with respect to the weights or gradient with respect to the bias. Okay, so anyway, you are computing the past running average of the gradients and the past running average of the squared gradients. That's essentially MTBTU, right? Then based on this MTBT, then we come up with the MT hat, VT hat, and then we update theta, remember, is representing our model parameters, so then we update the W or the biases. So if you take a look at it in terms of the code,
What would be the optimum learning rate to start with? 0.1 or 0.001 in Adam?
0.01.
0.1, right?
Yeah, because when I try 0.1, it doesn't.
Yeah, I was going.
yeah, that, see, these are called hyperparameters. So for example, if you, so I had a PhD student who spent 3 years I'll quickly show you because that paper, in my opinion, is very good and very important. So, okay, anyway, so you can see, like, so this is the paper, framework for designing architectures of. Since you guys asked, I'll just briefly comment on it. Okay, so anyway, the key idea, even though this was related to CNNs, which is our next topic, but the key idea was how do we design an optimal architecture and which always includes hyperparameters, such as the learning rate is one of them. In case of CNNs, we have what are called the kernels that we need, how many kernels to use, how many feature maps to use. So there's a lot of variables in designing an optimal architecture. So what Saleh and I did is we came up with a way to set it up as an optimization problem, and then so that we can within a short amount of time, because it takes tremendous amount of time to train a network, so we can't be just experimenting, okay, let's try 0.01, let's try 0.015, let's try 0.02, right? Anyway, so towards the end of the course, then once you have a better idea, I'll cover the main idea, but basically this will let us know what is a good hyperparameter for tuning an architecture. Okay. Anyway, back to the Atom. So the implementation is very easy. It just follows the equations that you guys saw for the MT, for the VT. For the GT, remember GT in their term basically means the gradient. But here we have two gradients. So GTW and GTB, one for the weight, for the on the bias. So in the beginning, I picked the gradient for the weight, store it in here, store it in the bias. And then this is exact implementation according to the paper. And then basically we update the weights and biases exactly as the paper said. And if you did it properly, you'll find this, like I said, is extremely fast. You only need 10 epochs to get to roughly 90% accuracy. Okay. So as you can see, I'm running it for 10 epochs, learning rate 0.01, Atom,
Where are the
and
beta 1 and beta 2?
oh, those are hard-coded in the
Oh,
code. I
hard-coded.
just left it as comment it out one more line, because that creates the network. Yeah, I don't need 50. 10, 10. So anyway, so within 10 epochs, it will hopefully come up pretty close. And you can see some 90% accuracy, and the error drops down to 18 within 10 epochs. Anyway, I'll give you the code, the derivation. So your job is to make sure if you were unable to do it, go through, understand it, and try to do it, right? Okay. One question, let me also share it with you. Michael had asked me in an email was, remember we were doing the softmax derivation? Okay, when we did the softmax, softmax, as you know, is only used in the last layer, because its job is to enhance the output that we wanted to be recognized better than the rest of the other outputs, right? So we wanted to come up with the delta computation inside the last neuron. And if you recall, the final answer was pretty easy. I forgot, it was like y minus s or something, right? Or s minus y, something like that. Okay, but that was based on cross entropy as the loss function. But what if we change the loss function to mean square error? Then how will this delta become? Anyway, after Michael asked me that question, I said, okay, let me see, would it come out to be a simpler thing, or would it be a little more involved? So I'll also put this on the website. So okay, so what I'll do is I added one more page over here. The first 3 pages you guys have already gone through, hopefully make sense. Okay, the last page over here is using the mean squared error. So if this is the loss function, okay, so again, I'll let you go through it, make sure I didn't make a mistake. Okay. So anyway, same idea, have a picture in front, because then you can see what gradients need to be accumulated. And again, I picked one example that if we can make it work for one example, then we can generalize it later. Okay. So in the beginning, it seems like it's very complex. It turns out quite a few equations over here, but if we then start thinking about it, try to express it in matrix form, then my analysis was that this will turn out to be what y is our expected output, y transpose s minus s transpose s. S is the output of the, if you recall, the softmax, which is basically e raised power over e to the s1 plus e to the s2 and so on. Okay. So anyway, that's the summary I came up with, provided I didn't make a mistake. So as an exercise, your job will be go through it, confirm I didn't make a mistake, and let me know. Okay. So now, let me use this. Okay. Let me go 5-10 more minutes, then I'll give you a break. Okay, so now let's come to our next topic, and our next topic is okay, so convolutional neural networks. Okay, so far we've learned how, so far we have looked at dense neural networks. Okay, where, as we discussed, we have one hidden layer. Right? We have some inputs. These feed to all the neurons. We have some output layer. Okay, and all of these go everywhere. Okay, we also discussed the universal approximation theorem. Okay, and according to the universal approximation theorem, we learned that even if the decision boundary is very complicated, okay, between the different classes, all we have to do is increase or reduce the number of neurons in the hidden layer. So the universal approximation theorem says any complex function can be learned by simply having enough neurons in the hidden layer, right? So as a result, should we be creating networks where, let's say we have multiple layers? Okay, will this give us any better accuracy as compared to just playing with the number of neurons in the hidden layer? And the answer is no, because the universal approximation theorem says even if it gives you slightly better accuracy, you come back over here, you increase or reduce the number of neurons, and you'll get the same accuracy. Okay. So why should we go in the direction of deeper networks? Okay, the whole title of this course is deep learning, so why should we even go beyond one layer? Okay, and the answer is everybody thought there's no need for these until around, I forgot, late 90s. LeCun, I think, is the one who came up with this concept of CNNs. Okay. So, in my opinion, he should be given a Nobel Prize because even though once we understand it, it's like it makes sense, but how did somebody come up with this? As you've seen with even the simple neural networks that you've been playing with, right? How long does it take to really prove your concept is correct? Let's take a look at batch norm, okay? And that's relatively trivial compared to CNNs or some of the networks that we'll see later. Anyway, so concept is not difficult, but programming of it, and you guys will program it, okay? In my opinion, you cannot call yourself good in deep learning until you have programmed a CNN one time, okay? You thought batch norm was hard. Wait till you get over here. Okay. Anyway, but the nice thing is once you do it, then you start to really understand how complex networks can be put together. Then after this, like I said, I'll introduce TensorFlow to you guys so that you guys can now be productive and start creating some very, very state-of-the-art type of results.